I'd like to start off by saying a little bit more about doping and how we get the correct number of carriers for the current we would like. So when we dope a material, we introduce tiny amounts of another material into our semiconductor, but the amount is so small, in just parts per million, that we still call the material by its element or name, say silicon or germanium. But we do have to think carefully about which material can be used to dope our semiconductor. So this slide is looking at what we do if we want to have an N-type material, because we want more electrons for conduction than holes. Therefore, we'd need to introduce a material which can generate an extra conducting electron. If our host material is silicon, which is in group 4, and we want to generate N-type silicon, we can add a small amount of dopant material from group 5. And that group 5 material has 5 bonding electrons in its outer shell. One element in group 5 that's regularly used for doping silicon, which is from group 4 in this way, is arsenic. And phosphorus can also be used. Now, when arsenic is introduced, or any group 5 atom that's suitable, the arsenic atoms replace a small proportion of the silicon atoms. However, since silicon only has 4 bonds or bonding electrons, this is the replacement atom drawn here in red, but silicon only has 4 bonds it needs to share, and arsenic has 5. This means the 5th electron, the 5th arsenic electron, is not needed for bonding. It's very weakly bound to the arsenic atom when it's in silicon, and this means that with only a tiny amount of energy, an amount which exists at room temperature, this 5th electron can leave and be free to conduct in the silicon crystal. It becomes it becomes a conducting electron. Now, this is represented by the electrons from arsenic having energy states very close to the conduction band, as you can see them in here. And this shows that the energy required to raise the electron to the conduction band is very small. Now, this is very different to intrinsic silicon, where the electrons would need to raise enough energy to cross its much larger band gap here. So that's obviously a larger amount of energy required than that. The same situation occurs with every arsenic atom introduced. And in this way, we can control the number of extra electrons introduced by silicon by controlling the number, or rather the concentration, of arsenic atoms that we put in. And this concentration is known as the doping concentration. And it's an important variable in this module and for the design of devices, because it determines the number of carriers and therefore the conductivity of the material and the current. In practice, some arsenic atoms may not donate an electron, but for our module in the second year, we're going to assume that each dopant atom generates 1 extra free carrier. And doping is a really important technique because it allows a semiconductor to exist which has more of one type of carrier than the other. Note that when doping with silicon, or doping silicon with arsenic, only excess electrons have been generated. It's also important to understand that the charge associated with arsenic atoms is actually positive. Firstly, since the arsenic atoms have donated electrons to the silicon semiconductor, we call them donor atoms. So sometimes we work out the donor concentration. But secondly, because the atoms have lost a charge, they've lost this electron that's gone off, one of their electrons, they no longer have an equal number of electrons and protons. And that means that overall, this arsenic ion here, this group 5 atom, has a positive charge associated with it now. And this is important because unlike mobile conducting electrons, these arsenic ions are stationary. Now, excess electrons are generated from the donor atoms, and so we call the donor atoms donors for short. And the concentration of donors introduced is usually referred to as ND, that's N subscript little d. Again, it's measured in cubic centimetres. All concentration in semiconductor devices are quantified as densities in cubic centimetres. So it will make sense when we do our calculations to use centimetres for all the parameters, including dimensions. And this does require quite a lot of conversion of units because most devices are much smaller than centimetres. But it also makes sense to use centimetres because carrier mobilities are also generally given as centimetres squared per volt second. Now, once the semiconductor is doped, as it is here, we refer to it as extrinsic because it's no longer pure or intrinsic. The process for generating additional conducting electrons is very effective, and so we can introduce a large number. And in fact, the concentration of electrons introduced from doping is far larger than the concentration of conduction electrons that are present in the intrinsic semiconductor because of the difference in band gap. And this means that we can write ND, the doping concentration, gives you a lot more carriers than the intrinsic carrier concentration. And because of this, we can approximate that the number of electrons in an N-type material is equal to the donor concentration. Nn is equal to capital N subscript D. So here, the subscript, this little subscript here means that we're in N-type material. So we're just approximating that the number of electrons in the N-type material is equal to the doping concentration of electrons. Now, this isn't quite accurate because some of the extra electrons will combine with holes that are present. However, the number of donated electrons tends to be so high compared with the loss of electrons that this still remains a fair approximation. But because some of the holes have recombined with electrons, it also means that the number of holes in an N-type semiconductor is less than the concentration of holes in an intrinsic semiconductor. In other words, the number of holes in an N-type semiconductor is less than the intrinsic number of holes in an undoped semiconductor. And so this is really highlighting that when a semiconductor is doped, the overall number of free carriers remains constant, not just in the intrinsic semiconductor case, as you learned in stage 1, but in a doped semiconductor too. So it's the law of mass action that electrons multiplied by the holes is equal to the intrinsic carrier concentration squared, where N is the electron concentration, P the hole concentration, and Ni intrinsic carrier concentration squared. And for an N-type semiconductor, we'd say the number of electrons in the N-type semiconductor multiplied by the number of holes in the semiconductor is still equal to Ni squared. It still remains constant. So this means that if we know the doping concentration, which we do because we set it as a design parameter, then we can calculate the number of conducting electrons and conducting holes in order to calculate the current, since Ni is a constant for a given material. And we're going to see and use this throughout the course. So a very similar process and theory exists for generating P-type material, which has more holes than electrons. If we move on to the P-type material here, we'll see that material from group 3 would need to be used to dope a group 4 material, such as silicon. Atoms from group 3 elements only have 3 bonded electrons in their outer shell, and therefore when the group 3 material, such as boron, is introduced into silicon, not all the bonds between the boron and silicon are satisfied or shared. And so you can envisage an additional electron is required from the silicon crystal lattice in order to enable the boron to become bonded with the silicon. Okay? So it's taken silicon, an electron from the silicon, and this results in a hole being generated from the valence in the valence band. So the generation of holes in the valence band with just a little amount of energy, one that's available at room temperature, is understood by the energy states being introduced by boron atoms being very close to the valence band here, valence band edge, and that's what you see here. These energy levels are very close to the valence band. The amount is available at room temperature, okay, in order to generate the holes. And again, for each boron atom introduced, it can be assumed that an additional hole is created. And this is really how the introduction of impurities generates P-type material. The boron atoms now have an additional electron, the boron atoms now have an additional electron associated with them. Sorry, so I'm going to go here, okay. They've got this extra electron, and so the boron atom becomes a negative ion. And these negative boron ions are located in the p-type material and form part of the crystal structure. They're not mobile. Because the boron atoms are generating holes by effectively accepting electrons from the silicon, we call them acceptor atoms, and therefore they tend to be called, the number of acceptor atoms introduced is called Na. You mustn't confuse these symbols representing doping, Na and Nd, with the effective densities of state in the conduction and valence band, which we call Nc and Nv. So just put those in brackets. And also, of course, don't confuse them with the density of conduction charge carriers, which we call N for the electrons and P for the holes. Those are the holes in the valence band, and N is the electrons in the conduction band. The doping concentration is Na and Nd. I'd like to make just one last point on doping, and that is, while it's also possible to introduce impurities into both metals and insulators, for metals there's so many carriers already available for conduction that the impact of these extra ones from doping would not generally be detectable. For insulators with large band gaps, there's defect states that exist in the band gap, and these tend to trap excess carriers rather than promoting them to the higher energy level where they could contribute to conduction. And so consequently, only semiconductors tend to really demonstrate the very wide range of conductivities through varying the doping level, which we saw on that graph. So that's what this next question is really saying, that I think you'd need to copy down. Why can't you dope so metals and insulators? Well, you can, but it's just not an effective process. So the next section I'd really like to begin is talking about the conduction mechanisms in solids. There's two main ways a current can flow that we're going to go through. Firstly, there's the drift current, and secondly, the diffusion current. The drift current is the one that should be familiar to most people on some level, but the diffusion current may not have been introduced to you since it's a current flow mechanism that only really occurs in a semiconductor. So if we begin with the drift current, I think that when we think of a drift current, I would imagine most people probably think of Ohm's law, which is given here by J is equal to sigma E, where J is the current density measured in amps per cross-sectional unit area, which, as I said, is in our case usually centimeters squared. Sigma is the conductivity of the material, and we've seen the factors and parameters that affect that already. And E is the electric field applied to the material. And so often we see that it's written as V equals IR as well, where V is the voltage applied to the material, I is the current flow, and R is the resistance of the material. If you remember, R is equal to rho L over A, here where R, or rather the rho, is the resistivity, the inverse of conductivity, L the length of the material, and A again the cross-sectional area of the material through which the current is flowing. So these equations show that when an electric field is applied, a proportional current flows, and they define the conductivity of a material as being the current density per unit electric field. That's what it's really saying. And this holds true really for all conductors, whether they're metals or semiconductors. The description of having a current flow due to the application of an electric field is really describing the drift current. And it's called this because the electric field causes the carrier to drift in one direction. The carriers are drifting under the force of the electric field. The speed of the carriers, which are drifting, can be estimated as around 100 meters a second. However, in addition to their drift speed, the carriers are also moving randomly due to the collisions, and this movement has a much higher velocity at around 10 to the 6 meters per second. And so then there's the question, well, how does this really help us calculate the current? Well, the current flow through a solid due to the application of this electric field is going to then be dependent on the electric charge E, the electron velocity V, and the carrier density per unit volume, which is N. So you can put this together to work out the drift current, which we're going to call J now. And J, you can see that J is equal to ENV. The carrier mobility, mu, relates the carrier velocity, V, down here now, to the applied electric field, E, by this equation number 4. So if you remember, this mu, mobility, is different for each material and it's different for electrons and holes. So in fact, this equation 4 gives us a definition of mobility as being the velocity per unit of electric field. So if we then substitute this expression for carrier velocity into the equation for current density, which was equation 3 here, we get equation 5. Okay, J equals En mu electric E times the electric field. Now we know that Ne mu or En mu in equation 5 is equal to the conductivity of the material. So we substitute the conductivity in equation 6 and we get J equals sigma E, which is Ohm's law. One thing that is very important to remember is that in semiconductors, both electrons and holes contribute to the material's conducting properties. And so we must write the conductivity sigma as being the sum of the electron and hole conductivities, as shown here in this equation here. The first part is for electrons, the second part is for holes. N is the electron density in the material and P is the hole density in the material, both in per cubic centimetres. The subscripts N and P used for the mobility terms are because we're looking at the electron and hole mobilities, which are different even though the materials are the same. And so we need to make sure we show that we're talking about electron mobility, which has the subscript N, and hole mobility, which has the subscript P. Although this is the full definition of conductivity in a material, it's worth pointing out that in most semiconductors, one of the terms in brackets dominates, either that due to the initial one here, due to electrons, or the second one due to holes, because the material is doped, and this can dramatically increase the concentration of electrons or holes relative to the other one. So usually just one dominates, and we'll come on to that too. So I'm now going to talk a little bit about the diffusion currents. So the diffusion current is the second type of current we really need to consider in semiconductor devices. And this current arises because of an uneven distribution of charge carriers in the semiconductor. And if there's an uneven distribution of electrons or holes, such as in the vicinity of a p-n junction, then carriers are going to diffuse from the high concentration regions to the low concentration regions, just as all species move from high concentration to low concentration. And that's what this next graph is really showing. It's just a very simple diagram showing an increasing concentration of electrons with increasing distance x along the graph. Now the electrons are going to move down the concentration gradient this way, as you can see, towards the left, because the constant gradient is positive. The movement of electrons, which are charges, constitutes a current, and therefore it plays an important role in semiconductor devices. A moving charge gives you a current. It's important to note that this movement of carriers is actually occurring without the application of any external field though, and that's why it's very different to the drift currents. So we have to look at what it depends on, and we will see that the diffusion current is going to depend on electrons moving down the concentration gradient, the electronic charge, which is E, and a diffusion coefficient, which we call D. And this diffusion coefficient is characteristic of the diffusion process for a particular material. And so we can then write for electrons, the current density, again given by J, is equal to minus E dN minus dN over dx. Or simplifying that by cancelling the negative signs, we write J E dN dN over dx, and this is equation 9. I'm going to pause for a moment there And then we'll come back on to putting the drift and diffusion current together in a little bit.